or like I'm missing out for like pros and cons wise.
Something I've just remembered, Kay, which we talked about in the beginning, but I'd forgotten about as this went on. One of the bigger problems, one of the bigger problems in designing the rear box is not just whether the drivetrain can actually fit in the box, but whether you can put it into the box when it's outside.
Right.
And currently it doesn't look like that can be done with the larger sprocket. So I know it's something we talked about, but kind of forgot about. So on your next iteration, I would include some sort of analysis of like whether this thing could slide through an open tube section.
Oh, right. That's good. I forgot about that too. Cool.
Yeah, it would also be helpful to get a quick sense for how much mass you're adding with these different configurations. It's not too hard to just, like you don't have to do any of the trims, but just assign the correct profile to these tubes and do a quick like mass properties just to see, oh, you know, we're increasing the mass by this much or that much. I think you'll find that these blue tubes, which are 0.65 wall, they add up pretty quick.
Okay. Yeah, because those are like heavier. Interesting.
You don't even have to create the tubes. You can just pull the length and then do it by linear density. That's a good point, though, John.
Yeah, good point. Okay. Okay, I can move on then. So for next steps, definitely create more configurations and play around with geometry and like account for the feedback. When it comes to evaluating the configurations, I would compare suspension stiffnesses to the baseline stiffnesses, like I mentioned earlier, and how I kind of estimate that was doing 3,000 pounds force on like the end of a beam. So it's modeling if the suspension is directly on the node. So, and I just found like a stiffness value and then compare that with the hand calcs of the other configurations, whether like if it's close to that or not close to that. And then also compare the weight like we were talking earlier. And then eventually narrow options down for potential anti-simulation if it's like under 80 frequency. So yeah, is there anything I missed or my process that I'm doing wrong or whatever? Like, yeah.
I have a question.
Yeah.
So I guess we have a pretty good way of judging the dynamic stiffness of the thing because we're looking for, you said it was more than 80 hertz natural frequency or something like that, right?
Mm-hmm.
What I'm wondering is, do we have an idea of like what a good value is for static stiffness? Like the 188,000 pounds per inch here. How do we like evaluate whether that's good enough?
We can't.
Yeah, I think that number is like, to get a good number, you would need a lot of testing data and maybe a driver who knows what they're doing. Because ultimately, like the reason why you don't want deflection is because you don't want it to change your geometry as your chassis is being loaded in whatever which way. But really, like to know how, like what is enough kind of depends on you having a driver who's able to tell. Like a baseline, like is like, hey, you know, maybe we don't want the toe of the tire to change, which is like the angle that it points, because that could cause some pretty unexpected driving characteristics. But like the degree to which that is important is something that is very difficult to quantify. Okay, I have a question for the baseline stiffness. Are you saying that you have a beam and you're loading it axially and then you're just measuring the displacement?
Yeah, just in compression, that's all.
I think it is slightly different for the chassis because while yes, all of the tubes are going to be in compression or tension, ideally if they're loaded at the nodes. If you think about it in 3D, it's going to be the sum of those tension and compression forces equals that force that's coming in, right? So if you do a little bit of trig, you'll find that the magnitude of the force is going to be A lot higher. Oh, I guess it doesn't really matter, right? Because it's the stiffness. Yeah.
Yeah,
Yeah,
the
there
goal
you
here
go.
was just to get a representative stiffness of what's the best we can do, which is just a lateral tube. And then the worst we can do is no lateral tube. And so talking with Kay, we kind of decided that like as long as we're between those two, we're probably fine because we don't know where we need to be. Like we can't be stiffer than at a node, and we couldn't be any floppier than getting rid of a tube entirely, which was the decision that was made last year.
Specifically for that third node,
Yeah.
third node that was near the tube.
Yeah.
Yeah, I think it might be helpful to look at, I think we played around with this last year, no? With like, all right, if there's this much deflection in that node, especially because that node is close to where the toe link mounts to, I think it's very valuable to look at how much that node is deflecting. And like, let's just assume that the toe link doesn't change in length at all. How much toe angle does that account to? And I'm sure you could find some references. I know Claude has a video where he's talking about how sensitive you want your toe angle to be.
Okay, cool. So just like figure out how much the angle would change and as like another like reference thing.
Yeah, if that's not too difficult. I can see that being quickly becoming a deep, dark rabbit hole that maybe is not worth going down.
I did it last year. It's pretty time consuming. The goal here with what Kay was doing was that like we had a way to like quickly evaluate the iterations of like, and the best way to do that was just like, what's the like basic lateral stiffness of each node that we have? Like we wanted to evaluate the suspension like the stiffness of the suspension points, since we're moving them away from the nodes and making them floppier. And so the quickest way to do that is just to like do a quick hand calc, beam calc, axial compression. And the idea is to land closer to a design that's better and then do ANSYS on that.
Yeah, I guess to Xander's point, I don't, yeah, I guess evaluating that takes a long time, but the as close as possible is kind of a sus thing, but I guess you're gonna have to do some weird analysis at some point.
Yeah, well, it's not as close as possible. Like we're not gonna get close to a lateral tube if it's not at a lateral tube. And so the idea was just try and understand what the scale is, where like lateral tube is at the stiff end and then no lateral tube is at the bottom end. And then, because like the math we're doing here is not going to be right. Like it's just not.
It's
like,
more of just to compare between designs.
Yeah. Like a lateral tube is going to be a lot stiffer when you have 3 other tubes coming into it perpendicularly. Not a lot stiffer, but it'll be stiffer.
I like no lateral tube. You're just looking at the stiffness and like of this rear box in like one direction, right?
Yeah.
Is that the same direction that was the least stiff for the last year's rear box? Or is that I guess like are you like taking into consideration all stiffness in other directions beyond it just lateral? No.
Okay, I don't know if you want to answer this one, but I can take it if you don't want to.
Well, I mean, like lateral direction and also like the harmonic part eventually, but that was my plan.
Yeah, the chassis is least stiff with this design is least stiff in the lateral direction. And in changing the design, we're trying to maintain some amount of stiff. Like we don't want to make it worse. And so we know what bad is and we know what good is. And so we just want to make sure our design lands somewhere in the middle, or K's design lands somewhere in the middle. And so the idea behind evaluating only the lateral stiffness is that as we move the tubes, like we're largely only moving the tubes laterally. So we're only really going to be changing, longitudinally. And so the way that we're moving it, we're largely only changing the lateral stiffness, and the stiffness of your suspension system affects handling characteristics more than anything. And so lateral stiffness is going to be the best evaluation method for like, I believe that that's the direction in which the stiffness makes the most impact to your handling, because the stiffness changes how quick your force transfers from different corners of the car, which is mostly happening when you're turning or quickly switching directions left to right.
Gotcha.
Real quick, Kay, is there another presentation for suspension, or is it just this?
Yes, yes.
There is. Okay. So we have another about 25 to 30 minutes left in suspension. Just want to let you know. Also, I am recording this, but I just wanted to make sure everyone is comfortable with that. If you're not, then I will stop and delete the recording. Sorry, I should have asked earlier. Okay, cool. Sorry for the interruption. Continue.
Sorry, do we have was there a time limit or something? All right, sorry. Anyway, today Jung-Ho and I will be presenting a section of our Confluence page dedicated to Tune to Win, which is a book that the suspension and aero team have been reading through. Next slide, please. So for the Confluence page, the objectives were to teach the younger people, the underclassmen who are going to be coming into the team, about just the basics of building a car and being able to like pass on the knowledge. We'd also like to understand the different interactions that take place in the car while the car's in motion, and understanding that there's trade-offs between pretty much everything you do and seeing how one thing can affect something else. And lastly, we'd like to create a guide that's really easily understandable by everyone, so that while building the car, you can have this like baseline to work off of. And I just sent the Confluence link in the chat for everyone to look at. Hopefully at the end, we'll be able to walk you guys through the page for a bit. Next slide, please.
All right, so the Tune to Win book is essentially this really long book, long but detailed book about various components of a race car. That includes the suspension systems, how weight distribution works, what happens when a car is going through a corner. There's aerodynamics and the effect of like tire pressure and size, the camber, what John was talking earlier about, toe in, toe out, all that good stuff. It would take way too long to touch on every single topic right now. We haven't even gone through every single topic, so I'm going to talk about one example, which is the slip angle. So what the slip angle is usually when a car is cornering, the tires of the car and the direction that it's traveling is actually not parallel. They're actually deviate away from each other, and that creates an angle, which we call the slip angle. What happens in that instance is that there's a contact patch where the tire is meeting the road that actually deforms. The tire adheres to the road and causes the tire to deform a certain amount. After the tire keeps rolling, that section of tire does go back to its original shape because tires are elastic and they're made of rubber. While this might sound like a horrible thing and you might want to avoid it at all costs, this is actually what we do want because it provides adequate adhesion to the road and grip, because we do want grip in a corner. And if you look at the graph on the right, you'll see the correlation between how much slip angle and how much friction that it provides. There's this range of slip angle that provides the most grip on the road, and that's usually where we want to be. Any more, any less, and you'll start compromising on how much grip you have going into a corner, coming out of a corner. Yeah, that's just one example out of various topics that are in this book. And like Shamama said, we're trying to go through everything and create a Confluence page where everyone can just skim through. And if they do want to know more about it, they can go read the actual book. But next slide, please.
Good question. Is there a way like teams can control slip angle so you have ultimately like such that you have the optimal grip as you're making turns?
That's what the steering wheel's for. Sorry, that was a cheeky answer.
Right, but but you can also overturn, right? Like it's not like you're going to maintain the right range of slip angle route.
Jung-Ho, do you want to try and tackle this one? I can also answer it.
So the question is how do you try and maintain that certain slip angle as much as possible?
Yeah. I'm just curious about the thing.
Well, you can even before you take steering into account, you can modify the tires with different softness, different types of tires, and all that. But again, like, I mean, Kyle did say just steering, but I feel like that's actually a very large part of it. Good drivers are able to steer very well by maintaining that certain slip angle. That's why they're professionals. Yeah, I don't know. Kyle, do you want to add to that?
Yeah. What was your question again? I've forgotten the wording. Sorry.
Yeah, so like what I'm thinking about is like for coefficient friction and slip ratio, you can like effectively measure slip ratio and then like control, like use traction control basically to ensure that you have like a certain level of grip. I'm just curious if that's something you can also apply to the slip angle. I don't know if that's necessarily true or not.
Kind of. In your example of traction control, in the example of traction control, you have your slip ratio, how much force you're generating, how slow, how much and like your acceleration due to that force. But none of that affects your direction. And so you have kind of a tricky thing when your slip angle is similar thing. Your slip angle dictates how much force you generate, which dictates how much acceleration. But as that changes, your like the direction in which you're pointing the car changes. And so it's a little more difficult to like have a system that tries to monitor that. You could do it. It's not really necessary. There's also one thing that's important to like as an engineer, you're like, oh, maximize the force. That's better, right? But it's not always the best idea to be at your peak slip force or at your peak slip angle for force. Designing for that can actually make a car that's really hard to drive. Because most of the time that you make up in a race is not exactly how fast you're going through the most, the tightest bit of the corner. It's more about how you enter and exit the corner and whether or not you're able to brake late into the corner and accelerate quickly out of the corner. So in this case, it's more important to make a car that handles really well. And so this graph is actually a great example that Jongho has up, which is a graph of coefficient of friction versus slip angle. And this like okay, they're all dashed. The one with a tight peak at the top, will generate a huge amount of cornering force. But what you'll actually find is due to the quick roundover in terms of how much force gets generated is that when you're at peak force, very, very small, if you get a gust of wind or you change your steering angle slightly or you hit a bump or something, you'll get very different amounts of lateral force. And so the car will be really squirrely in the corners. And so a tire like this would be great for NASCAR, where you really, really just need to make the most out of your cornering performance. And you can kind of be on that edge, on that knife edge. But these other two tires with a flatter top, this flat top on the graph is actually a really good thing for handling. So this flat top, you can stay at a high force while also making kind of directional inputs without it being a sensitive system. And then also how the graph acts on the roll off, like when you start to lose force, like you turn too much and you start to lose force, being able to feel that and catch it is really important as a driver. And so theoretically you could do some crazy engineering, but only in very controlled situations. It's better to design a car that is less sensitive and slightly less performative because you'll actually get more out of the car.
Awesome. Sweet, that makes a lot of sense. Thank you.
This is a fact that actually applies everywhere in the car. Like it's generally better for the system to be a little less sensitive and a little less performative because you'll be able to drive it harder. Particularly because we're not expert racing drivers who are used to very tight sensitive systems.
I got a question here. Why the heck does coefficient of friction go down for small slip angles?
Small slip angles?
Yeah.
It's saying that it's highlighting a very interesting point. I don't know if Shamama or Jongho you wanna talk about that, about what that means, that at zero slip angle the coefficient of friction is 0. It's highlighting a very interesting point though.
I think the scales will, oh never mind, that is 0. Weird. Okay.
Coefficient of friction is also a bit of a misnomer. It's the ratio of lateral force to normal force. Purely lateral force.
Very different from the number I was thinking of.
Yeah, and
But essentially what that's saying is that in order for your car to turn or to accelerate at all in the lateral direction, your tires need to slip. There's no case ever ever where your car is not slipping. It's always slipping. Isn't that crazy? It is.
All right, so for our next steps, we'd like to do our best to make the Confluence easier to navigate and to read. We'd also like to make a glossary a lot bigger so that people who haven't read the book before and who don't know a lot about cars will be able to understand all of it. And lastly, we'd like to incorporate any feedback we get from this review into our Confluence page. If we had the time, I'd like to share my screen and give you guys an overview of the page. All right.
You've got 15 minutes, so definitely.
Right. If everyone can see this, so we start off with the overview of the book and the table of contents right here. And then here we have just imagery of what the suspension looks like in a car. And here's some definitions like we mentioned. And then this is where the notes start for, we start off with the chapter headings and they're divided into a lot of subsections. So there's definitely a lot here. We tried to put in like as many diagrams and stuff as we could, but it's still definitely a lot of reading. And yeah, so if we can get any feedback on how to improve readability or the page in general, please let us know.
If we still have a minute, I have a question that I should really know the answer to. What's the difference between oversteer and a driver who just steers too much?
Nothing.
Okay.
I mean, drifting is just controlled oversteer.
It's just, I hear sometimes that it's like people talk about oversteer as something inherent to the car.
It is. So like
Okay.
a car, like if you're in a corner, just like flying through the corner, and let's say like you're at the maximum amount of force your tires can take. If you apply just a little more power and you go just a little faster, you're going to break traction. And whether or not you brake at the front or the rear first kind of is part of what defines whether a car is an understeer car or an oversteer car. So like a car an oversteer car is a car that tends to oversteer before it'll understeer. Like when you start to break traction, the back will go out and not the front sliding.
Yeah, an important like vehicle dynamics lesson for everybody is that the reason, if you look at like our formula car, that one time where we got stickers telling us where the weight distribution is, the front to back weight distribution is like pretty dang close to 50-50. It's like a few percent off. And the reason why is because the closer your center of mass is to neutral, like smack in the middle of your wheelbase, the closer your car will be to neutral steer, which is the tendency to kind of, the car will kind of point in the direction, will go in the direction you point it. And if you let it be, it will stay there. It won't self-correct, it won't oversteer, it won't understeer, it'll just kind of go. If your car is heavy in the rear, it will oversteer. It will tend to oversteer because your rear end it takes more force for your rear end to round the corner, and that will give you the tendency to oversteer.
You can also change understeer, oversteer characteristics just based on the sizes of your wheels as well.
Cool. So we're going to talk about aerodynamics. This is me, Avery, and Brohill. It's been an interesting time. Next slide. So we're focusing on just like very generally the aerodynamics of the car. So we're starting off with the nose cone because we know that that's like a thing that we need to have on the car to cover the impact attenuator, because the rules say, hey, you should have a thing. So the like very minimum of this is cover the impact attenuator and don't increase drag. And we'll talk about some of the design considerations in a minute. Those are like the very basics. So we're just kind of figuring out how do we CAD a thing that goes on the front of the car. And then ideally, the next step beyond that is decreasing the drag of the car compared to like just a sphere or like a basic shape to try to do some CFD. And that's where the aerodynamics part comes in. And then if we get to it, we'll be designing a rear diffuser to put on the back of the car under the rear box to decrease drag and maybe increase downforce. That's like a little bit of a reach goal. Next slide.
Oh, I have one quick thing to say. This is pretty nitpicky, but there are additional rules surrounding like the nose cone and the front of the cockpit. Your minimum requirement is more than just covering the impact attenuator.
Yeah, we're gonna talk about that.
Okay, okay.
So yeah, just as a like very basic general overview. Yeah. So our goals for this design review are to document the process so far, show like where we're at right now and where we're going forward, and then of course get feedback about design considerations and our next steps and things like that. So next slide, Avery.
Yeah, so we started at the beginning of the semester by doing some CAD just to get a feel for how difficult making this would be. So the impact attenuator was designed based on the rules, which I think you can find on our Confluence page if you're interested. That was pretty simple to CAD. But then we started doing some surface modeling and we created our first preliminary aero assembly. As you can see, it's not as easy as it might seem. So here are our sort of first day preliminary nose cone sketches. These are informed by some of the front radius requirements from the rules. So we, so the rules say that forward-facing edges have to have a 5 millimeter minimum radius and a 3 millimeter radius for vertical edges. But they also say that for body work, which is what we could consider the nose cone, the forward-facing radii is a minimum of 38 millimeters. So depending on whether we consider it a aerodynamic device or not, that front radius will change. And so, yeah, that's sort of some of the things that we took into consideration with this first sketch. Next slide. However,
got that sketch actually. Jesus. Is that sketch just being pulled off of the like hoop that goes over the steering wheel? Is that what I'm seeing?
I believe that's the front box. I'm not sure the exact name for it.
It's the edge of the dashboard, basically, that hoop.
Okay.
Yeah.
Okay. The geometry just looks a little weird. Keep in mind, like it looks like it slopes down faster than the actual like chassis slopes down. Like I don't.
This was we're trying to sort of demonstrate like our overall process. This is in no way, shape, or form our like finalized geometry.
Okay, I'm just checking. Also, keep in mind the sketches that designate the hoops have a 1-inch tube around them. So if you're drawing to the tube or to the sketch, it's not going to fit.
Yeah, this was an offset path from that center.
Yeah, I believe we offsetted by whatever the radius was.
Okay, I just want to check.
Yep,
Yeah.
thank you.
I think to Kyle's point, like even if this is pointing out your process, this is going to be kind of nitpicky, but like, even though this is just pointing out your process, part of your process should be, you need to be looking at more than just the front hoop. You need to be looking at the tubes that consist the cockpit, because that's like the main thing that you need to work around, right?
Yeah, of course. And I think this is some of the stuff that we were facing. So after going in on the first day and trying to do CAD, we realized that it was a lot more difficult than we had first thought. And in general, we were struggling to justify some of our design decisions in terms of surface modeling. Obviously, that first sketch was not informed well by the structure of the car. So in general, we decided to go back and do some research. We looked at a few papers and basically summarized the key takeaways from them, which you can find in more detail on our Confluence page. But our main takeaways were minimizing drag is a factor, but doesn't matter as long as it's not a parachute. And I think Rohil will talk a little bit more about how we got that from Aurora. Downforce won't be generated, but try to minimize lift. And then sort of counterintuitively, we want air to go under the car to improve the under tray performance. I believe that's called the ground effect, that phenomenon of like sucking the car into the ground to get more downforce. And then the stagnation point, which from a CFD perspective is sort of where the lines will separate as they go around the nose cone, should be placed near the tip of the nose to avoid a line basically going backwards and around the tip and then up over the top. Yeah, I think that's it for the main takeaways.
Cool. Yeah. So another thing, after we did some research, we're like, hey, based on the research we found, it seemed like there was not a whole lot of aerodynamic thought process put into other teams' designs of the nose cone specifically. So we reached out to Aurora, who, for those of you who don't know, is a former member of the team who graduated last year. And we asked for some advice on the process they went through last year. So a couple of the key factors were the key factors pretty much centered around convenience and not creating any problems. So for one, we would want the nose cone to hug the car. We don't want it to like be jutting out or anything. Two, we want it to be easily attached and removable. That makes for better serviceability and is overall a good thing to have in design. And then three, the nose cone is like the front of the car. It's made out of composites and it contains all like the livery, the stickers, stuff like that. So it's a relatively large aesthetic statement. So that was another priority. Lower on the list, something they didn't even actually end up doing last year was using CFD. Just because the main purpose of the nose cone is not, like Avery mentioned earlier, it's not really an aerodynamic device per se. It's not meant to produce force. It's primarily to like keep drag to a relative minimum. So to that end, the main takeaway from using CFD for a nose cone would be just ensuring that streamlines don't separate from the body and the flow stays attached to the body.
Isn't that
I have a
different
quick
from
question. Oh, go ahead, Justin.
I was just gonna ask, like, isn't that different from what you mentioned here, where it says the stagnation point should be placed near the tip of the nose cone? Like, I think like Avery might explain the stagnation points of where those flow lines like do separate.
Yeah. Oh yeah. So I think what Avery was talking about was like how they separate to go up like over the car and under the car. What I'm talking about with not separating is that like as the flow goes over the car let's say, it doesn't like, it stays, the streamlines stay the same distance away from the surface across the length of the car.
Gotcha.
It's basically turbulence is kind of what that means.
I have two quick questions. With this research that you did to find that minimizing drag is a factor but doesn't matter, what is like the range of coefficient of drags that you found in your research? Like what is the range of CDs that we're looking at here? Like,
sure. I don't think we saw CDs necessarily. So one of the issues we had was just looking at the research that exists out there. What teams have done in the past is not really well quantitatively justified. We have a few papers on our Confluence, which you can take a look at if you're interested, but these were like the biggest real qualitative takeaways we could derive, and the other, there just wasn't that much in terms of quantitative stuff. Laura, you were going to say something?
So I was just going to point to the page under aerodynamics, under nose cone, there's a background research page. The top paper was kind of the most influential, where they did CFD on nose cones based on rocket nose cones, because those decrease drag and don't need to produce downforce. And kind of the analysis they did was, let's take a bunch of different equations, they had 4 different options, and put them into CFD and then pick whichever one has the lowest drag coefficient, but they weren't all very far apart. So they picked the lowest one and it was like the best at reducing drag, but it wasn't like amazing stellar. It was just the lowest of the numbers. And I didn't write down the numbers, that's on me. But the paper is on there as well.
Cool. Yeah, I think it's worthwhile to do at least like a 2D CFD if it's not too hard to get a ballpark sense for what the CD of any given nose cone shape is. And then to the point of like, oh, if you want to maximize airflow, that's another thing that you can look at with CFD, and that could tell you generally like, hey, I want the shape to be roughly like this, like where the nose is slanted up or slanted down or whatever. I think CFD will help you answer these questions.
Yes, and we in the next steps we are planning to go into 2D CFD. If you're interested in the CDs, I just found them. They're like 0.4 to 0.6 roughly. Yeah.
I had 2 quick things. One, Avery, you were talking about minimum radius of curvature on the nose. Make sure, like, don't shoot for the minimum. Like, take the minimum, add like 10 millimeters or something like that. Like, it's not going to be a performance hit at all. And if we're under that radius, that's like a $4,000 mistake. They could be fixed. Like, they will measure it.
It's not a $4,000 mistake. It's you get to competition and you pass inspection, but wait, you don't pass inspection and you can't race because your nose cone is just a little bit too small. Yeah. It's a huge, it's like the worst way to go.
Time to take out the hammer.
We
Duct tape.
We have little circles. We have really tiny little circles in this CAD. We were just kind of like drawing like a parabola or like a spline and comparing it to the nose cone or to the minimum radius circle with just like, I think we were doing by how far out it was on last year's, and the minimum radius of like a spline that we could get was nowhere near minimum rules radius. So.
Okay, just be careful because the spline that's on screen right now looks smaller than the minimum radius.
Yeah, that was a little bit of.
Okay. The second thing. What was I gonna say? Yeah, on the radius thing, just keep in mind, like when they manufacture it, it's gonna be a little different. Also, like you've got a big heavy panel on top that's gonna droop down and it's gonna pull that radius just a little bit tighter. My second point, through your research of looking at other teams' nose cones, did you find anything that other teams have done that we could do that might minimize pain in designing, manufacturing expense, all of that? Because we had a lot of pain with like all of our body work being composites. And so we saw other teams using airframe fabric and we're like, hell, like let's do that. It's like mad cheap, super easy, super quick, and we don't have to make a bunch of stuff. Was there anything like that that you guys saw while you're doing your research? Probably not.
Laurel or Avery, do you want to speak to this? I don't recall seeing anything, but I also did not do like a deep dive through the research.
Yeah, I was reading a paper specifically about how they set up their CFD. So we have like a whole table of how they did CFD, but they didn't talk about construction.
Fair enough.
For that particular paper. There is another one that I don't know if we read that might include it.
The
But
carbon one.
What did you say, Avery?
Are you talking about the carbon composites paper?
Oh yeah, that one.
I don't think we got through that.
Just a real quick question, since I haven't ever actually seen a car in person. What else creates downforce? Like you said that downforce isn't really created by the nose cone. What else on the car is used to create downforce?
So, Laurel, go ahead.
Oh, okay. For us, kind of not much, like the weight of the car. Other devices you can use are the under tray. You can shape it so that there's the Bernoulli effect, the ground effect that Avery mentioned. A diffuser will also help with that. Front and rear wings. If you look up an FSAE car on the internet, they use massive, massive wings. That's just like entirely downforce. But we don't have any of those.
Just a quick note, you all have about 5 minutes left. So if you could sort of move on, that'd be great.
Cool. If there are no more questions, yeah, I'll start here. Cool. So we've been working through a couple other things aside from design, which have taken up a bit of time. So yeah, one thing is Star CCM. Licensing for software is always a time. But I think there is some light at the end of the tunnel. It seems like we're almost done. We have access to the software. We have access to download it. We really just need to check out licenses from Olin's server. And we have instructions on how to do that. So I think we're pretty close, but I don't want to say we are done until we're done. And then we were also looking into quoting of Mark V parts just because there might be some potential complications. Kitty Hawk was supposed to construct them for us, but with limited access to the shop due to COVID, we're not sure what's going to happen with that. So we were trying to figure out a backup. And we got quotes back from Custom Composites, the shop we use in Maine. It came out to about $2,000 for the nose cone, $600 for the rear diffuser, which is like more optional. We can see where we're at in terms of finances. It was $500 for the materials based on what he quoted, but I think the quotes were for 3 parts rather than 2. So I'd say more like $300, $400 range for materials. And lead times, he wasn't super specific, but he said a few weeks. So we can.
Oh, sorry. Okay.
Yeah, I was just going to say, so we like don't have to jump on it right now, I think, since it's not a number of months.
Gotcha. Did we ever make molds for the nose cone Mark V, or is this quote, does this quote also include the molds for that?
The quote includes the molds, yeah.
Got it. Got it.
Yep. And then last but not least, we are working, we're making sure to track our progress in Confluence. We have a pretty comprehensive design log. We need to continue updating our reference page with summaries of the papers. And then we also need to build out the nose cone page to be more comprehensive as we go through designs. We've started a bit of that, but it's super rough right now. So we need to go through and add all the relevant rules, CAD screenshots, et cetera, as we go through our design. Next slide, please.
Real quick, when you talk to Custom Composites, they knew that like they sponsored us before, like we're getting their like cheap rates, right?
I don't know if, so I mentioned that I had gotten the contact from Aurora. I told them who we were. Yeah, but I didn't like mention that they were a sponsor per se. I did check these prices with Aurora and she said they seem pretty reasonable.
Okay.
Not sure if they're like heavily discounted or something, but they don't, like they seem relatively reasonable.
Okay.
And happy to talk through that more offline with you if you'd like to go into detail or if there needs to be more.
If Aurora says they're reasonable, then that sounds pretty good.
Okay, cool.
By the way, just for context, is the story here something like we used to have plans to do in-house layups and then we abandoned it? Because when I was looking through the container, I saw a lot of carbon fiber that it sounds like we're not using.
Sure. So I don't think we ever planned to do an in-house layup of the nose cone. I think we were thinking about doing an in-house layup for the rear diffuser. That's a lot simpler of a part. So I think that's probably the zone you were seeing.
Yeah, once upon a time, we got a lot of free carbon fiber. And what was supposed to happen is we were supposed to get the mold from Kitty Hawk, take that along with our carbon fiber up to Custom Composites in Maine. And then like all they're helping us with is like putting it on the thing and like curing it and whatever, yada, yada, and taking it back to Olin. So like a lot of the stuff would be kind of free because Kitty Hawk is free, the material is free. But if Custom Composites is like gonna have to be involved in a more substantial way, then I guess 2K is the price.
Cool. Yeah, last slide. So in terms of next steps, I think like we mentioned earlier, we started off fast and then realized that we had a sort of weak foundation and went back, did some research. I think we're in a relatively good place where we know that like some parts of the design don't need to be super specific and aero is not like vital here. So I think our next steps are sort of go back to SolidWorks, start creating the sketches, like the profile sketches, guide curves, etc. Model the surfaces, fine tune those surfaces to ensure smoothness between different parts, like different parts of the surface in SolidWorks, and then go ahead and add all necessary tabs and hardware. After we do that, we're probably going to go to CFD, whether that ends up being like a 3D star CCM or a more 2D like X-foil type thing. It remains to be seen. And then, yeah, we want to make sure to expand the Confluence documentation, like I stated. Cool. Are there any questions?
Kyle, to your point, I think the rules say that you need some kind of like solid enclosure to make sure that like the driver's legs don't hit the ground and like nothing from the outside can come into the cockpit. So like, I guess if you really wanted to, you could have like a weird looking thing where your impact attenuator is just hanging out in the open and you only wrap the cockpit.
We get airframe fabric the cockpit, or like you do like a shorty nose cone that just like to the front.
The airframe fabric the driver?
Yeah.
But then
saran wrap them.
Oh, perfect.
Yeah.
I did have one question. Are we allowed to reuse nose cones year to year? And if we are, do we want to specifically design this nose cone to be easier to reuse next year? Because like a couple $1,000s for a nose cone is a lot. Like that's most of the cost of a chassis.
Mm.
There is basically like 2 instances of the words nose cone in the rules. So like 1 or 2, I forget. So like they're not very specific about like a nose cone specifically. They just kind of say like, if you have something that you're calling a nose cone that is like an aerodynamic device, then it's this. And if it's not, it's this. And beyond that, there's kind of not a lot.
Yeah.
So there's no rule against it.
In terms of,
might be able to reuse it.
Yeah, I think that's a question like that I would have for y'all. The process that we were sort of going through with this project is making sure that like the nose cone is the main aero component on the car, right? Like rear diffuser, other stuff like that doesn't matter as much. So we wanted to make sure that we had the ability to design one. But if let's say we end up designing it and this year and we want to reuse the one from last year on Mark 6 and then maybe use our design on the next iteration of the vehicle when we can construct it, not during COVID, and get all the help from custom and from Kitty Hawk, that could make sense. But yeah, I think that might be a good conversation to have.
Yeah, I don't think it would be the worst idea to just add 1/2 inch in every dimension to the chassis just to make it a little bigger so that next year's car and next car we make it a nose cone for, we can just, because like the aerodynamic like loss from like even if you made it 1 inch wider on either side, it like pales in comparison to the amount of turbulence generated by the wheels. Like the amount of turbulence generated by the wheels on open wheel cars is ridiculous. And like the frontal area of the wheels is almost more than the nose cone.
Okay, so you're thinking design it to be larger, and then what would the tab? Would it just be that the tabs change or something to accommodate?
The tabs wouldn't even have to change. You could glue spacers onto the inside of the nose cone if that would be easier. No, like I'm saying, like if you like assemble it and epoxy the spacers in place so that it just fits. Because I think the tabs are welded on the chassis. I'm not sure about that one.
Yeah, or even if like I think like the rules say that you need to have significant design changes. So if you use the same nose cone, I think that's fine. Like I don't think like and like one step down from that is like maybe you just use the same molds every year, and then you do a layup, which is, I mean, it's pretty tedious, but it's way easier than having to CAD a new one, and it's still a lot cheaper because molds are pretty expensive.
For clarification, the major design changes, is that on a vehicle level or on like a part by part level? Or like a subsystem
What's
level?
the boat? Is it Theseus's boat or something?
Yeah, ship a Theseus. Yeah,
Change every part of a boat. Is it the same boat?
Yeah, we're really getting to some heavy philosophical talk, but I think it's fair to say that some parts of the car can be reused from year to year. Like we don't
Yeah.
Like it is not intended that you build a new car from scratch every year. Because if that was the case, it wouldn't be. Yeah, there would not be as many teams as there are, I think.
Cool.
Yeah, and I just checked under front chassis protection, the only thing that you're required to have is an impact attenuator and an anti-intrusion plate in that entire section. Obviously, I haven't read the entire rules, but
Yeah, there's more, but
yeah.
Also,
Can I quickly run to the bathroom like 10 seconds?
Yeah, Justin, run to the bathroom. We can take a quick break before drivetrain gets going.
Yeah, that's so great.
Get hyped.
Come on, Xander, spoiling the end of WandaVision. Give it all away.
It's fair play.
Vague spoilers at most.
We're having a bio break. Okay, let me go get an avocado.
Okay. Wait, how does she have avocados?
I don't know. That's a good question.
What?
How does Emily have avocados? Maybe I guess she could have gone into town. and
Whole
maybe
Foods?
gotten-
I don't know. There's like transnational shipping / trucking lines that you've got a
That's
farm in
not what I
California,
mean.
and then there's like a truck.
Emily, people want to know, how do you have an avocado?
Avocados from Mexico?
How?
Yeah, where'd you get it?
Instacart.
Hmm.
Okay.
Oh, you meant the end of the supply chain.
I love avocados. Do you guys eat avocados raw? Because I love eating avocados raw.
Avocados in general just have like
Put
that
their
gross
avocados.
squishy feel.
Huh?
Yeah, I
What'd you
just
say?
don't like
haven't
avocados.
had a
Sean,
good
I cannot
avocado.
express how wrong you are.
They're just
All
like
right,
A good
Sean,
avocado?
come to California and have a good avocado.
I've been to
There's
California.
avocados in
and I've had
Massachusetts.
avocados.
Avocados should be like mushy, Ishan.
Yeah,
The
they
avocados
should
in
be mushy.
Massachusetts are like every single one I have had is worse than the ones in California. because
I've
they have to
I've
go
had
in a truck.
avocados in California, but like they still just like have that like nasty.
Have you had a ripe avocado? Specifically
Yes,
a
I've
ripe
Also
one?
not like
No,
lettuce.
he's specifically.
Oh, it says it's from
All right,
Mexico.
y'all.
Okay,
I
I'm
mean,
sorry.
like, yes, but California is like closer to Mexico than Massachusetts is.
Right.
Ready. Welcome all to the drivetrain portion of the design review. Woo! We all good to go? All right, Emily, I think you're first.
I don't think Kyle's back yet. If that's
Oh, okay. Yeah, let's wait for Kyle.
You can immediately know someone's from California by asking their opinion on avocados and artichokes. Because no one else has an opinion on them.
Artichokes.
Artichokes are
the
amazing.
best.
See?
I don't have an opinion on artichokes, but I have
You
an
are
opinion
sure.
on avocados.
My town literally has a restaurant that is a tourist trap because of artichokes.
What? What does that even mean?
It's called Duart's Tavern. Their thing is a lullaberry pie and artichoke soup. Lullaberries are also a specifically California thing.
I've
Yeah,
never had artichoke.
Also, artichokes are a vessel for butter. Like that's their only purpose.
This
I
definitely
don't
reminds me
know how
of,
to eat. How do you eat these?
If the drivetrain slides are slated to take like an hour and 15 minutes or hour and 10, we should probably just get started now, and Kyle will miss what he misses.
Yeah,
just
looks like
in the
Kyle's
interest of time.
back.
Oh, look at that.
We should get moving.
Okay.
Alrighty.
Yeah. Yeah. Okay, next slide, please. My project is a push bar. Okay, next slide, please. Oh, okay. Sorry, I was looking at my other screen. Okay. So essentially the push bar, its goal is to kind of lift the back of the car, and then the wheels of the push bar act as like external wheels and basically allows the car to move while the car is off. And my goal this semester was to redesign the push bar so that 2 people could use it comfortably and take in some user feedback and improve the user experience of the push bar. Yeah. So these are some of the design requirements. There weren't a lot. I think one of the most important things to keep in mind is that I have to account that 2 people should be able to use the push bar at the same time. Yeah. Next slide, please. Okay, so to the right is a beautiful drawing by Justin that explains the current our current push bar design. So as you can see, like there's like little U hooks on the push bar, and those essentially attach to a jacking point, which is part of the car. It's on like the back of the car, which is that orange bar. So it attaches underneath, and it should lift the car up a little bit, and then that's how we're able to push the car. So to the left are some points of improvement or pain points that I've gathered after talking to a bunch of members on the team that have used the push bar. So it was awkward to push with two people. It was flexible, so like it bent at some places, which I don't think is what you want in a push bar. And it also wasn't able to stand upright. So if you leaned it against the wall, it would like tip and fall, which wasn't very nice for people using it. The jacking point was also difficult to locate and attach to. So like the U-hooks, it wasn't as easy to get the U-hooks underneath the jacking point. And then it was also an odd shape, so that made storage kind of difficult. But yeah. Next slide, please. Okay, so these are some designs that I was thinking of. So there's a 4-bar linkage design that was inspired by Owen, who also had this project last year. But I also included his CAD. My design isn't exactly like his CAD, but I thought it was the clearest example of it because my drawings are kind of like janky. But essentially, something nice about the 4-bar linkage is that if 2 points are held at these places, like the top bar will like stay parallel. So that would make like attaching to the jacking point a lot easier and nicer. So like you just need to simply like pull it up a little bit more so that's perpendicular, and then it would lift the car up. Yeah. So the pros of this design is that it should be easy to use. So it's just like one pulling motion to like to rotate the 4-bar linkage to be in the right position. It'd be nice to make it adjustable so you can add like different jacking points on and then change the height of the 4-bar linkage. And then also this design is stiffer than the current push bars design because there'll be 2 bars supporting it. Some cons, by adding the 4-bar linkage, that's just adding complexity. It also might be costlier because you need a pulling mechanism, which I'll explain like in the next slide why we need a mechanism to pull up the 4-bar linkage. And there might be added weight with the extra parts. Another feature that I was considering for the push bar is adding collapsibility feature. So like that long, so this is like, imagine that this is the push bar. So like, because this is such like an odd area, like storage is not easy. So like if we're able to like collapse it on itself or make it like a really slim line, I thought that would make like storing it a lot easier. So like that little whiteboard drawing is like one way I was considering how to add that collapsibility feature. Is just adding like a bar in between the L, which would also make it a lot sturdier. But yeah.
One thing I want to point out, I like this link of this list of pros and cons. I would say that a lighter push bar is better than a heavier one that is equal on all other fronts, but we care about weight very little. So you shouldn't feel like, I think that's like one of the, like you should care very little about it because it's not like we're gonna go racing with the push bar. So if it needs to be stiffer, just slap more metal on it. If it needs to be more compact because like you want it to fold, like it doesn't matter if it's heavier, basically.
Okay, yeah, for sure.
It pales in comparison to the weight of the car, so it's
It's far better for this thing to be overbuilt because it'll likely be tossed around.
Yeah.
Okay.
Yeah.
That's really helpful to keep in mind. Thank you.
I had a quick note. Picking up the rear of the car is really convenient. It's not a requirement, I don't think. And a lot of other teams actually use push bars that just push on the main hoop, which I think might be a good idea. There's no wheels, there's no lifting mechanism. You don't have to twist it, because one of the problems right now with the push bar is that the act of pushing on it actually unhooks it from the chassis, which is really, 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 really frustrating. And a push bar that pushes on the main hoop will actually be totally flat. So your storage problems go away. If you Google FSA push bar, you'll see a lot of teams using a push bar that literally just like is like a rectangular opening that slots over the main hoop. Some of them have bracing for that goes to like diagonal members on the hoop, on the supporting the hoop. But I feel bad because you've done a lot of really good design work here and a lot of really good thinking, and like but I think moving to a bar like that will save us a lot of effort, and it makes it's really easy to store. The utility of being able to pick up the car is nice, though the rear wheels don't add a lot of drag when you're pushing it around. It's primarily the front wheels.
Thank you. Yeah. Next slide. Okay, so these are some hand calculations, really rough hand calculations that I did to calculate like the minimum force that we would need to like pull the 4-bar linkage with the car on top of it, like in the U hook things. So like on the very top is like a color-coded design of the 4-bar linkage. And then like on the bottom is like all the different parts broken down, or like all the forces that I thought were going to be acting on each bar. And then the green one is like a sum of like all those forces, which is essentially just the force of the car, and then the force of the tension. But yeah, after all those calculations, I found that like the minimum force that we would need to pull that 4-bar linkage would be 5,935 newtons. And before I thought that we could just like pull it up, like someone really strong could just like pull the thing, but then I was like, I can barely lift 30 pounds. So I think that would be very difficult. So yeah, next slide. So some next steps were to investigate like different options for pulling of the 4-bar linkage. We were considering some like pulley mechanism or like a winch, a little picture on the right. And then I was also going to start developing CAD for the design and revisit the dimensions, because a lot of the dimensions that I was using were based off of last year or some of Owen's designs, which I think is the current push bars designs too. So I think revisiting those dimensions would be nice in optimizing the design. And then I wanted to work on some FEA to see if it was like even possible to use the 4-bar linkage or even like the collapsibility feature. But yeah. And then next step is just like, next slide. Please. I was just gonna seek advice on how to make the calculations more accurate. If I needed to make it more accurate, I don't really know. Also, if there were any suggestions for the pulling mechanisms, and then some resources to learn how to FEA. But yeah, that's it. Thank you.
This is a random note that you should, I can't believe I haven't told you, mentioned this yet, but the full car CAD, like if you just open it and like figure out, like measure like what's the distance from the bottom of the wheel to the rear bar, that is not the real distance. It's like because the car sinks down, right, because of the suspension. And so there is an actual distance, and that's a plane somewhere in the CAD that John probably knows the name of. Don't design it to like that, the dimension I just mentioned, because that's what Alex did 3 years ago or 4 years ago, and that push bar was terrible.
Oh, I definitely did that, but it's okay.
So I'm glad I'm telling you now. The top plane.
In the CAD, the top plane is the ground plane.
Okay.
I have one thing, like the one thing I think that Kyle's push bar cannot do that our push bar hypothetically can do but can't do very well is there's a little swivel wheel on ours. So if you like tilt it back even more, you can turn your car kind of on a dime. Like the pivot point is roughly in the middle of, like, it's between your two front wheels. So if you really want to maneuver your car through a tight spot, that's pretty handy. But also the push bar that we have is like so loosey goosey and so awful that like it's kind of sketchy to do that. But like that is one advantage of having something like going that route as opposed to like the clip onto the top main hoop strategy.
Otherwise, you need someone inside the actual driver's seat, like steering, right?
Yeah,
You always
do
do.
need someone inside the car.
Yeah. Okay.
Yeah, I was gonna about the like over top thing. I was gonna ask about width, like having two people standing outside of the wheels or like on the sides of the car seems harder to get through narrow spots than two people standing in the back.
The bar just goes all the way back. The bar goes like
Oh, okay.
5 feet back to the rear of the car. I think you almost always have to push from the rear of the car when you're using a push bar. I was gonna say, you did a really good job here, Emily. You've done some really good calculations and some really good design work. I would urge you to take a step back from the calculations and especially moving into FEA or ANSYS to evaluate whether the complexity of this design is worth being able to pick up the rear of the car. I think there's a lot of good learning utility here that you've done, but I don't know if this design decision is, or this design path is worth being able to pick up the rear of the car. John made a really good point about being able to like spin the car, though we don't do that very often. If you do decide to go with a pick up the car, kind of scooping under the car push bar, please, please, please do a free body diagram of someone pushing on the car, because you have to push with a considerable amount of force. And what happens with the push bar is you usually have to push down as much as you're pushing forward just to keep it from popping out. And so if you were to design a push bar that actually engaged with the bar differently, such that you could just push forward without it coming out off the car, that would be amazing. But I would encourage you to check out the design pathway that is interfacing with the main hoop, because I think it solves a lot of your problems.
Yeah, for sure.
You did a really good job here, though. Great drawings. They're really helpful.
Agreed. Yeah, I think doing a quick Google search for like these just to get like inspiration is, there's like a lot of cool stuff out there. Yeah, good work.
Ready. Great. Cool. Let's talk about the gearbox next. Next slide, please. So some context here. This semester, we have a few people working on designing and manufacturing in-house over here a gearbox transmission. So we're using this semester as a chance to explore a whole new region of design space for a formula transmission. And we think this might be an exciting alternative to the chain-based designs we've used in the past. Next slide. So our goals with this project are to learn how to design a gearbox with formula relevant specifications. So we're sticking to the same motor and gear ratio, although we haven't quite made a final decision on the differential yet. Throughout the project, we'll be trying to assess the advantages of this transmission type over the Mark V style transmission we've been using. And we also want to get a sense for what the pain points are with this type of design, because we're sure there are plenty. Coming out of this project, we want the ability to compare chain and gear systems when we're deciding what our next transmission looks like. We want some amount of design heritage that could be reused if we choose to pursue gearboxes further. And we want to actually end up with, at the end of the semester, a gearbox with spinning output shafts and a good mass, efficiency, packaging potential, all the stuff that entails designing for a car which needs to be light and efficient. Our goals for this design review in particular is we're going to present our early configuration choices, and then we have some design and in-progress decisions which we'd like feedback on, which we'd like to present.
Yeah, so we started out looking at the different types of gearboxes / transmission systems that we could use to move the energy from the motor to the differential. And so we looked at planetary gearboxes, since that's something that a lot of teams have used. A lot of those planetary gearboxes, the way that they're set up is you put them directly in the wheel. Since they have the concentric shaft coming out of the motor, they just drop them in the suspension, and they do software differentials, and that works, except that wasn't really in the scope for what we wanted to do. And it would also be really expensive, because then you need two motors, one for each wheel. We have a chain drive, which we've done in the past. And one of the things that was a big problem with that in the past was it would pop, or there's just a lot of force on the chain because it's pulling. And so that was something that we wanted to think about, but we were trying to explore different options, so we were likely not going to do. Then there's a linear gearbox with a chain. So instead of doing just a chain drive, you do a small linear gearbox, and then you do a chain drive to your final output. That way you do less of a reduction on the chain. But the problem with this is you're going to still have around the same amount of force on that chain, since it's going to be your final output to just move the motion. And same with a planetary gearbox to chain. And so then the final design that we thought we could do was a linear gearbox, where we have a series of gears that move the motion from the motor to the transmission, but also do a reduction. And we did the decision matrix, which you can see here, and we tried to evaluate all of them on toughness, cost, manufacturability, packaging, and configurability. And we set weights to them, and we found that the linear gearbox seemed to be the best in theory.
What is toughness? Is that like reliability?
Pretty much. Yep. I should have spelled it with a UFFNESS.
A reason we rated the linear gearbox with chain and planetary gearbox with chain poorly in that category is if we set up a system where we have a gearbox connected to a chain connected to our output, we'd see all of the problems we have been seeing with dealing with chain systems, where we've broken a lot of chains in the past. Plus, then we'd see all the problems we'd expect to see with gearboxes, which presumably would lead to a fairly risky design or something that's more likely to fall apart.
Yeah.
I want to make 2 comments on this table. I think you're missing a couple of things that might be important to think about. One of which is repairability/replaceability. Yes, we have broken chains, but like we can go to any car parts store and buy a motorcycle chain that'll just go right on our thing. But if we mess up a gear, we're just out of the running. The other thing is rotational inertia of the system. A big part of the drivetrain's performance is its rotational inertia. And a really important factor in like how well we perform as an FSAE car is how well we can accelerate, because we don't have a lot of high-speed corners. It's a lot of speeding up very quickly and slowing down very quickly, very often. And so the rotational inertia is a big impact of like how much power we lose to the drivetrain. The other thing is, I think like the strength of a system and the robustness of a system are 2 different things that you've kind of wrapped into toughness. The way that we've been designing the chains, they've not been very strong, but they're very robust. You could probably put a pebble into a sprocket and it'll just go around with the chain and get spat out the other side. If you put a pebble in the gears, you're going to snap gear teeth off.
Right.
And then that goes into the repairability part of it. I just wanted to bring that up because gears worry me in that aspect.
Yep. So in the design slide that we talk about next, we'll talk a little bit more about like how we're going to be protecting these gears. One of the other things that came to mind when we did a linear gearbox, one of the things that we're looking into as a team is regen breaking. And from what I've read online and through the papers that we've seen, chain is just not great for regen breaking, because you're going to be putting force in one direction when you're driving, and then as soon as you regen brake, you're putting a force in the other direction, and that can easily make the chain pop. And so that's another reason why we were looking at the linear gearbox.
Yeah, I think Kyle's points are not like reasons why the linear gearbox is bad. It's just other things to look at. Like, right. For instance, the rotational inertia of the chain, or like any single stage thing, is going to be the worst out of all of the options. And to Kyle's point, I think one other thing that you touched on but didn't include in the table is like the complexity of a design. With it should have like a negative weighting. So like, for instance, having two MRACs, 208s, or like 4 in-hub motors is an incredibly complex design
right.
to pull off, and that should also be considered here, even though it sounds like you thought about it.
Yeah. In any case, with this decision made, I think some of these things, like Kyle, the point about rotational inertia is not something I thought about, so I've made a note of trying to measure that as we go on. It's gonna be really interesting. But it's also something that probably inherently comes with making a gearbox. So it's sort of like, once we've decided we're going to try out a gearbox, we're going to try it, and we're going to try to then pay attention to all these things that might go wrong, so that we can make a decision in the future.
Yeah, rotational inertia is a small one. I'm not worried about that. I am worried about the other things though.
Fair enough. Yeah. So next slide. This is the layout that we've chosen to roll with as a result of that decision in the past. So what we have is we have our motor, which is coupled to gears within the gearbox casing. We have a gear on a shaft. We have a two-stage geared transmission, which then transfers power to our differential. And then we have a set of plates that hold the motor in place and mount the differential. The sort of strategy here of having the differential poke into the gearbox a little bit was an interesting one. It's one that we sort of thought about for a little while about whether or not it would be possible. It's also something that we've seen other teams do before when we were reviewing how other teams couple their systems together. And it just turns out if you want to avoid having any chain going between your output stage of your gear and your differential, it's best to bolt the gear directly onto your differential and have the differential ride in bearings on the gearbox casing. The whole gearbox casing would probably be a two-part enclosure, which would be sealed, filled with oil, and would have an expansion valve for if the oil pressure gets too high. And the rest of the components we will talk about. Most of them we've had ideas for that we're working on. Any questions about this slide in particular? All right, Liz, take it away. Next slide, please.
Yeah, so we needed to choose if we wanted to do a spline or a key, and this part is the part that is going to attach to the motor. And so we did CAD for both a key and a spline, and we found that the key just would not, the factor of safety on the key was too small for the amount of torque that we will have. So we went with a spline instead. If you go to the next slide.
I have a quick question.
Yeah.
Is the 240, is that like Newton meters?
Yes.
And if so, where does that come from?
It's the max torque from the max.
Okay, thanks.
Yeah.
I just want to make a quick note.
Yeah.
Yeah, the factor of safety on the key design is that that's an artifact of your boundary conditions and your FEA most likely. Like that's probably not a realistic number. I would encourage you to find some resources on doing hand calcs for these. Keys and splines have been made for the last like 100 years, and I guarantee you there's like multiple books with calculations of how to do these. And that will almost certainly be more accurate than any FEA program will give you in terms of a number. I would encourage you to look at that. But good analysis here.
Okay. So we chose to go with a spline, and we found a spline shaft that came that we could buy from a company, a spline shaft that came with a hub within spline on the inside of the hub, but the hub wouldn't be able to attach straight to, because the hub that they made was too small to bolt right onto the so we made a hub to go in between. But this assumes that we couldn't make a spline at school, and if we could make a spline at school, then we'd be able to make a hub here at the school and just have one hub instead of two hubs. And the spline shaft here would come from the gearbox and insert into the hub on the MRAX.
All right, so we have our gearbox idea. Now we need to figure out which gears we're going to use. In previous years, Justin has calculated the ideal gear ratio to be 3.67 to 1, just based on the slippage of the wheels and some other factors. I just done some research and found that some teams use module 3 gears, which are like metric gears. And so I arbitrarily just said that we're going to use them. I still need to perform force calcs on them to make sure that they'll be able to handle the loads that we're going to put them under. But if other teams are able to use them, I would assume that we've got pretty similar characteristics to other teams. So hopefully they'll work out. I'm going to do the force calcs before we order anything or buy anything. And then we also knew that our motor is a certain diameter and our differential is a certain diameter. And about the closest that we wanted to bring them together would put their center to center to be around 7.5 inches. So that was our goal. We wanted to hit the gearbox distance center to center to be 7.5 inches. And using all of these parameters, we were able to make some gear selection.
Okay, I have a point to make here.
Yep.
Your weighting table had packaging as the most important factor. And it says here that you're gunning for 7.5 inches. And it seems like the closer you get to that small center to center, the better. I would argue that that's not necessarily the case. Like, packaging is inherently a multi-system thing. And so you cannot say that 7.5 center to center is better than anything else. And that's especially troubling because that's like what you claim to be the most important factor. I don't think it really changes much about your design, but I think that I would heavily call into question that goal as being optimal or like something to shoot for, because it seems like it's uninformed.
Okay. Yeah. I mean, we should look into where it's going to fit and whether having a larger center to center is a better idea. 7.5 was like the minimum that we could get it to, and it was just an arbitrary goal that we set. So based on the 7.5 inches, if we wanted to have a one-stage gearbox, that would require a huge gear to get the 3.67 to 1 and traverse that 7.5 inches. So they don't sell gears big enough to do that, at least for module 3. So we decided that we needed to do a 2-stage gear ratio. And I took the square root of 3.67. That way I would have 2 equal gear ratios that are 2 stages. And talking to Kyle, I wanted to have 2 relatively prime tooth numbers for the gears. That way they would have equal wear on them, since every tooth would come in contact with every tooth on the other gear. And so we came up with using a 23 tooth to a 45 tooth gear ratio, which if we do that twice gives us a ratio of 3.828 to 1. And it's better for us to be on the little higher end of the 3.67 to 1 than the lower end, since if there's any inefficiencies in the system, it will still be able to drive properly. Any questions on that part?
I have a question potentially for you, or maybe Justin, you can chime in, or Kyle. I feel like the cycle life that the Formula car sees in a season is pretty low, like low enough to the point where maybe we don't care about speccing gear teeth that are relatively prime. Would it be more important? Like, would it be better to have something that's closer to the gear ratio, the ideal gear ratio?
I can hit 3.67 to 1 exactly if we aren't doing relatively prime gears.
I would definitely prioritize packaging, performance, and other factors over having relatively prime gears, especially if they're enclosed and oiled. And given that we have such a short lifetime, I brought it up mostly because, like, here's the thing you should know. Did you think about it? And also having 2 even-toothed gears is particularly bad because it means that each tooth only touches 2 other teeth ever. And so if you have like a manufacturing defect or a hotspot, like anything that happens to one tooth, it's just gonna like consistently grate away at those 2 teeth, and you're just gonna get a problem area that forms, which probably outweighs nailing the gear ratio, because it's going to generate heat, it's going to generate stress, it's going to generate like shock loading in your transmission. It's not great.
Right.
But you make a good point, John.
On the performance aspect, that's also a great point. I think I still need to do some sensitivity analysis and how like much deviation from this ideal quote unquote gear ratio actually like matters. But kind of I think I could probably do that on the actual MATLAB analysis, but ideally once we have Mark V running, like we should have a much better understanding of how like accurate simulation is, or how much like simulation makes sense.
If we have time, I'd be really interested in changing the sprockets on Mark V to test different ratios and see if those match up with our model.
Yeah. One thing you can definitely do is, like, if you have the money for it, you can pick like basically just three points on our line, right? Or three sets of like gears, like one that like kind of where we think the ideal point is, one like far behind, one greater, and we can like show that like there's this relationship that like one lower gear ratio performs like I guess slightly worse than our ideal, and the greater one performs slightly worse, and we'll know.
So talking to Baja, because they've been using a linear gearbox forever, 2 big things that they did. They got their gears for $0.01 each because they got a sponsorship. So that's definitely something we can look at, because the supplier that I wanted to get from, just looking at who has the most number of gears and the gears that were sized for what we're looking for, is the same company that was sponsoring them. So I'm definitely going to reach out when we get ready to buy. So we could do different sets of gear ratios and try them out. The second thing is they did have a keyed shaft as their input, but they also are dealing with a lot less torque. But that was just an aside.
All of 10 horsepower.
Yeah.
I had two good points. One, if you're going to play around with your gear ratios a little more to try and hit 3.67 exactly, maybe take a look at not having 2 identical gear ratios, but having 2 that are close. You might find that you can get a better selection of gears or gear teeth numbers or something just by like changing that a little bit, because identical and close to identical are probably a negligible difference in performance and packaging.
So if we were to get a second set of gears, the one thing that we could do is get like 3 different gear ratios, because the spacing between the first and the second stage is going to be the same, the center to center. And so then we can play like, and just try out different combinations.
Yeah, another thing to note. Oh, sorry, you have another second.
Also, have you thought about the manufacturing and complexity of this actual gearbox? Because Baja machines theirs out of one piece of like several $100 aluminum. Like it's like a $400 block of aluminum that they machine it out of, which it's a lot of machining. Okay.
We'll get there.
The previous designs we could water jet, which you can't do because you need an enclosed box for the gears.
So the only thing that I've looked at in terms of machining is the actual gears itself. Baja had a lot of trouble actually machining the gears, but they were able to drill through them. So for that middle stage, we were going to screw them together and use shoulder bolts or whatever. That way we don't have to actually like machine a bigger hole or whatever, or a spline. For the first stage, John recommended taking a look at EDM into the gear. That way we could actually machine a spline shaft, like the reverse of the spline shaft in the center of it. And so that's something that's in my next steps.
Yeah. Also on the note of like buying a different like selection of gears, like make sure when you go and get gears for like your final design that you get like multiple in case like when we test them, like ideally one's that's going to fail, and so we'd like to have extra sets to replace afterwards. So note.
Also, if you're doing an oil filled container, please consider assembly and maintenance. If you don't have a way to change the oil and you just have to open it and let the oil drain everywhere, I would be very annoyed.
Baja's gearbox could not be taken apart, so we will
Yeah.
be better than that.
Yeah, I know.
Baja, well, it can. I did it. It's not
Oh.
fun. It takes like an hour and a lot of grease all over your hands, and they do have drain plugs, but they're not great. So yeah, learn lessons from them.
One more thing I wanted to mention about the comparison with Baja is it's part of why I was part of why I remain kind of skeptical of keyed shafts. Although I'll try to find some more literature on specifying those. But I know the slot way they've cut their key has failed, I think, twice now on their drive shaft in a situation with a lot less motor torque and fairly comparable shaft sizes. So, you know,
The one advantage to doing a keyed shaft, though, is we can find gears with the cutout for the key, which would make it a lot easier. We wouldn't have to wire EDM like a spline into it. But definitely
anyway, we should be talking about this next meeting. I just wanted to mention. All right, final thing to talk about here, and I know these sort of seem like a few sets of disjointed parts, but it's all slowly coming together. Is the motor mount. So it's that part in purple there, which connects this backing plate, which bolts onto the AMRAX with the rest of the gearbox. We need some sort of ideally lightweight connection between the gearbox and that back plate. The current design would be a cylinder, just in case of the motor. It doubles as a scatter shield, which is nice because we get to save on some complexity and mass there. And then on the flat surfaces on either side of the cylinder, we'd have a set of threaded holes for fastening. Currently, the design is, that's a good point from John. Currently, the design is fabricated from a standard off-the-shelf piece, 5-inch length of 10-inch outer diameter, 1/4-inch wall aluminum tube. So looking at the fastening requirements, we'd like to resist the nominal peak torque of the motor, which again is 240 Newton meters. So at the radius and proposed eight fastener bolt pattern, we could achieve the required clamping force with 832 screws with a pretty good factor of safety on that connection. And then some other things that can be done here is by turning down the diameter of the midsection of this bracket, we can further save on mass while also maintaining a strong structure. Next slide. I've done some analysis on what the loads on a part like this might look like, and it turns out that the vast majority of the loading and stress actually happens at the bolted connection points and is due to bolt preload, and isn't really due to the overall torque or acceleration of the motor. So what you see here is an FEA model of the system with refined mesh with the peak rated motor torque, as well as a 2G acceleration in the axial and lateral directions. So this would be 2Gs times the mass of the motor as the force that you might experience if you go over a bump. And someone should tell me if that is too low for expected shock on the chassis. But our factor of safety is quite high here, which leads to the question of could we narrow the midsection of this bracket further? Right now it's at 3 millimeters of wall thickness, which is the same thickness as the scatter shield for the Mark V. For the Mark V motor scatter shield. But I've also just heard recently that the actual lower bound for a scatter shield might be a lot lower, so we might be able to make that part smaller. As it stands, the part masses at 1.2 kilograms, which is fairly light for all that it's doing, scatter shield and bracketing combined. Some questions I have about this is, is it worth it to try to shave more mass off of this? It is already pretty light. Is lock wire okay as a model for positive retention of those fasteners around the outside? My idea would be there would be 4 pairs of 832s lock wired to each other. And then also, how do people feel about threading 832 holes into a quarter inch thick lip on that perimeter? And is there maybe a better way to do it?
I have a couple points on this.
Yeah, what's up?
One, anything out of aluminum that is under like regular cycling of loading, please look at the fatigue life of those parts. You could have a part that like works once, but could easily be, you could easily exceed its fatigue life. I would be highly dubious of 832s just into tapped aluminum. I think that's asking for trouble. Anytime you're screwing anything into tapped aluminum, kind of don't. It's like generally not a good idea. Like you have problems if you assemble it and then disassemble it and then assemble it again. Like you can have problems with wearing out your threads in the aluminum parts. I would also encourage you not just to look at the strength of a part under loading, like whether it like is too stressed, but also look at the stiffness of your system. You've chosen chain designs are highly chain designs you could like twist like 10 degrees and they'd still work. They're like they can deal with a lot of vibration, they can deal with a lot of motion. That's why they're used on motorcycles everywhere. Gears are not. Small amounts of deflection can cause big problems. And so please take a look at that.
Yeah, those are great points. Something to note is this is mounting the MRAX bracket in our general design. What we're rolling with so far is we have a splined or keyed shaft, probably spline sticking out of the gearbox, and we have a coupling in between that gearbox and the MRAX. So all of the bearings that maintain precise alignment for the gear interfaces would be contained within the gearbox. But that's definitely good stuff to think about. I think when we have a better model of what the gearbox side of things looks like, we'll start looking at harmonic studies and such to see what that kind of deflection would be. But yeah, fatigue's really interesting. I haven't seen a ton of resources on aluminum on how to really like computationally model aluminum fatigue. I know aluminum doesn't really have a formal fatigue floor. What would you recommend for like checking that out?
Yeah, so let me remember. Take a look at the SN curves for aluminum. There isn't a fatigue floor, but you can make some estimate for like loading frequency and like we run certain number of hours. You can like make an estimate. The stress to maintain a high fatigue life is surprisingly low in aluminum. The other thing is that SN curves are only for cyclic loading around a neutral axis or like a neutral load. So if you have a load that goes 5 pounds, -5 pounds, 5 pounds, -5 pounds, 5 pounds, -5 pounds, that's very different than if you have a load that goes 95, 105, 95, 105, 95, 105. And so there's ways to combine SN curves with like a variable, like a static load that's like 100 pounds, but varies by 5. You do some combination of like a static analysis of like, is it strong enough to withstand 100 pounds? And what's the lifetime for like a 10-pound peak to peak amplitude? And there's ways to kind of like do some rough like linear combination of those to get a lifetime estimate.
Yeah. I think what you're looking for there is like the Goodman diagram. I think the Goodman diagram incorporates the mean.
You spell it?
Goodman, Goodman.
Right,
and then yeah, what Kyle's talking about is the mean alternating stress varies. So it could be at 90 or 0.
Okay, yeah, I'll check that out. By the way, Kyle, if your concern is about the threads specifically on that surface, I wonder if you might feel comfier with a steel thread insert, like where you tap the thing out to a larger thread size, put in a steel insert, and that's your contact surface for the bolts that you're putting in and removing.
That's a pretty common way to thread things into aluminum.
Or could you just use lock nuts on the other side of it, or do you not have enough clearance?
That also
there's not enough clearance on the other side.
I'd also, if these are critical fasteners, I've dealt with this in the past and like never got a resolution. Where in the rules when it talks about critical fasteners, it requires I don't know, it requires like grade 8 or something, but grade 8 is not defined for anything lower than 1/4 inch.
Sorry,
if I'm remembering
correctly. You said gradient?
Grade 8.
Grade
it's just
8.
the bolt strength.
Sure.
And so it's a little, I was dealing with this on the suspension components where we were like, ah, feck it, like we'll just make everything 1/4-20 and it won't be a problem. So I would make sure that 832s actually qualify to be critical hardware. Though lock wire is definitely the way to.
Yeah,
tie
send
that
a
up.
rules clarification for that. That's like the only way that you'll be able to resolve that problem.
Yeah.
Really?
Also, really.
If it's
Yeah,
about,
'cause it's up to the judges, right?
Yeah.
yeah, okay.
It's a really good.
I know.
If you think
sorry,
832
go
is
ahead.
good, sorry. If it's a good rule of thumb. If you think 832 is the way to go, just upsize one. Like the amount of mass, like unless it causes like real design issues, it like will almost certainly save you a headache later, especially if you want to change any component of the design and it like creates different loads or weakens things later on down the line. It'll save you some effort.
Okay, I think the main concern here is bumping up the screw increases the wall thickness. Could start with larger stock and then turn it down farther. Of course, it's more manufacturing time.
One thing I was going to say is, how are you going to manufacture this? This is 10-inch OD is by far bigger than anything that we can do at Olin, right? Like,
is it bigger than our lathe?
It's way bigger than our lathe. I don't think you can do 10 inches on our lathe. I think you'd have to like maybe on one of the new CNC machines, you put it in there and then like, it's just like a really awful, I don't know.
I know how we do the top and bottom surfaces. I have a plan for that.
I just think that like, you should talk to the shop staff or something. Looking at this, I don't think you can make this at Olin, and it's like looks like a part that you need to outsource.
This looks like a bracket that is over designed to be a bracket. Like I don't mean that in an insulting way. Like it's a clean solution. But in terms of like its ability to make most of your vibrational loads on the motor and like from bumps and shit are going to be up and down. Most of your acceleration loads from the motor from accelerating and braking are going to be forwards and backwards. And so I think a bracket system that like better utilize just like vertical and horizontal elements, it's going to be a lot easier to manufacture. It's going to be a lot easier, well, maybe easier to assemble. It'll definitely be easier to manufacture and will probably better support your loads with less weight.
All right, well, I'll get in touch with the shop about that. On the weight issue, because we need a scatter shield for the motor anyway, if we can do this, it would be really cool. Because as it stands, this piece is already 2 pounds lighter than our scatter shield.
Okay, but our scatter shield. Let's not dwell on this for too long because we have to move on.
Yeah,
but our scatter shield is 3 times as thick as it needs to be. So,
all right. Yeah. Well, thanks for the input. I'll check all this stuff out.
I think one manufacturing method you could potentially look at is just like you large it those aluminum flanges, find some off-the-shelf component that's happens to fit that round tube need, or somehow roll and weld it, and then just weld those flanges on.
That would be pretty cool.
Please don't design aluminum parts that require welds to be structural. We can't do.
Also keep that in mind.
Okay. Anyhow. Oh, I guess that's me. All right, so I'm looking at the clock here, and I've got 4 minutes. So I'll just try to speed run through this. This is fine. Like this is mainly in the ideation phase anyway. So anyhow, yes, general idea overview purpose. Basically, the design of Mark V showed we had a lot on the answer questions. There's a lot of design assumptions made, such as like, can we get away with an ANSI 40 versus ANSI 50 chain? Like what chain tension should we use? And we basically just like forego that by just saying like, all of them. We'll just be able to like adjust for anything. But basically like testing these systems using the car requires dedicated test days, a lot of setup time, a lot of people, and then the entire car has to function. So those like pretty much make testing pretty rare. And so kind of to increase the output of tests and the possibility of tests we can run, we're looking for an off-the-car solution that will help us better understand our design assumptions and also support development of the car when the car is not fully built. And so some of the use cases I've listed out here that I think we could potentially run include measuring the efficiency and endurance of the gearbox, measuring the endurance of the chain, performance tensioner, so on. And then some cool opportunities in the future, like maybe testing out regenerative braking, doing some more like formal analysis on our brake rotors, and then like proper design if you want to shrink our tires, which is kind of like anyhow, concept design, pretty much the whole thing is going to be controlled by a laptop, which is connected to the Mark IV accumulator. The Mark IV accumulator will have to be it's called properly integrated. We'll talk about a little bit more later on, but also feature like a safety e-stop. But the Mark IV accumulator connects to the motor controller, connects to the MRX, all cooled by a cooling pump in the bucket water. And it's basically the motor and the shaft. Like there's a motor and a shaft of a flywheel, all held on a steel test bed frame covered by plexiglass. that's kind of like the overarching like look right now of what I'm thinking about designing. Big red button, yes. But okay, 2 more minutes. Let's kind of go by that. The test stand. This is really like I'm looking at just really like making a well steel structure. Ideally, I would have like a big steel plate with electric poles for mounting fixtures, but it's just too expensive. So I'm thinking about getting like steel tubing, welding them together, and welding down like L brackets, or we can bolt it down to surfaces, or eventually like use I guess sandbags to weigh it down. Electrical integration. I talked to Audie and Wesley. Basically, it's possible, but it's going to require 30 hours or so of work to actually make it usable. One option we thinking about is like making it a electrical lease training project for the summer. But we talk more about the electrical courses that are on. I think like that's in this last minute usefully, but I'd like to get more feedback. I think one of the main things I'd like to get more feedback on is specifically like test methodology of some of these tests that I want to run. Right now, it's all in the like early brainstorm stage. For instance, like this is a pretty cheap way to measure the efficiency of the gearbox. One way I'm thinking about doing it is like basically using the motor controller's reading of current voltage to calculate power in, but power out, it's like we don't have a dyno, so like I'm thinking about using a jank way where we use the relationship of power out is equal to torque times angular velocity. Yes, angular velocity, and then measure torque on the output of our gearbox by basically attaching the flywheel to it, the the output shaft, doing like a calibration test early on where we measure the moment of inertia by just like dropping a mass, or just using SolidWorks and comparing that to the SolidWorks calculated value, and then like taking those values, using a wheel speed sensor to measure the angular velocity of our flywheel, and then from there calculate a power out measurement. But yeah, like that's like a kind of a jank way to calculate efficiency, but so it's something I like those methodologies for like the majority of the other tests. Something I like to get more feedback on. I think I have a future debate probably. We're running out of time.
I have a question here.
Go ahead, Xander.
So you're saying for power out measurement, you're measuring your torque times your angular velocity. Do you have some way of measuring output torque while the thing's in motion?
Yeah, so that's what I'm saying is like we'll do a calibration test to figure out the moment of inertia of the gearbox plus the flywheel beforehand. So we have a known value for that. And then we'll have a wheel speed sensor that can measure angular velocity as it's just rotating. And so angular velocity, if you have a measurement of the angular velocity over time, you can figure out your angular acceleration, and then your angular acceleration and your moment of inertia give you torque.
Right, sorry, it's right there on the slide. Missed that.
I want to give you an idea. I got 2 things. One way you could measure torque is, and I don't know if this is done. I don't know if this is a COT solution. But if your connection between your motor and whatever else, or like some connection along the rotational pathway, if it's flexible, you can essentially like measure the like torsional stiffness of that flexure, and you can measure the flexure, like you can measure the twist of that thing in a lot of different ways. It is spinning, but like there's 101 different ways you could measure that. Not all of them are easy, but that's an idea if you wanted a way to measure torque. And the reason I bring that up is because I want to encourage you to explore other ways of absorbing energy besides a flywheel. With the power of our motor, you're going to need a really sizable flywheel, I think. Flywheels can also get dangerous pretty quickly, especially if they're not balanced properly. And I also think what is likely to happen in this scenario is your flywheel is going to get up to very high speeds very quickly. And the amount of time you actually have to take data is going to be low. And you're also not going to measure data under the circumstances in which the MRX is actually used. The MRX is largely used under like high load, low speed, like relatively low speed. Like we're not at the, we're usually not operating at the top end of the MRX. Like most of our top speed is like 70 miles an hour. And most of the time we're driving is under 30 miles an hour. And so I'd encourage you to like a dynamometer like this is essentially just, you just need something to absorb energy while it spins. And so I'd encourage you to take a look at different ways of doing that. Eddy currents, fluids, those are generally a lot more fail safe. And like if something goes wrong, if it's imbalanced, if yada yada, somebody sticks their finger in it, like it's usually less dangerous.
Yeah.
So
I think that, yeah, essentially, I think that would, yeah, this is like trying to figure out like a solution that's like requires a solution that's like outside design our own dyno. But I think if we were to make our own dyno, yeah, I think those two solutions you mentioned, like the eddy currents, fluids, and then there's also a third, like essentially making a brake dyno, where we just like, we kill the motor and just like brake, measure the force, and measure the energy there. I think that one's a potential, but I think like, I think that's a good point. I think we could potentially explore the option of actually designing and building a full-out dyno for this. But yeah, if this is like, I don't know how much we can stretch to, or that was a little more. I think we'll do that for sure.
No, you make a good point. Like those things are more difficult. Like this is definitely the easiest solution. Have you done the numbers to figure out like what size because like what you want is to size your flywheel so that it absorbs energy over a certain amount of time, and that time is dependent on like what you want to look at. And you also care, like you don't just care about like sweeping through the whole speed and power range of the motor. You care about like the rate at which the motor speed is changing, because if you're at a certain power for a certain amount of time, the performance is going to change, whether you're looking at like peak versus somewhat sustained power.
Right.
It depends on what you're trying to measure, but I'd encourage you to take a look at the sizing of this thing and see if it's feasible. I haven't done the math, but working with flywheels last semester, I was like, these things get big fast. Like 12-inch diameter ring, 50 pounds, like only absorbs a couple kilowatts.
Okay.
And it like that was at 60,000 RPM. So like,
oh, we dump a lot of kilowatts into this thing, don't we?
Yeah, our motor is 80 kilowatts.
80 kilowatts, yeah.
And so, like, yeah.
Okay, that's completely fair. I have not done the hand calc on that to check how feasible it is.
But before we go, I have like a bit of feedback. This is gonna be pretty harsh, actually, but on like the drivetrain, the gearbox project, if your goal is to fabricate it this semester, and if you count how many weeks there are left in the semester, there's not a lot. There's like 6, and like 5 maybe if you discount like the senior week, like finals week crunch time. There's just not a lot of time. And if you have a lot of missing parts, like, oh, are we going to buy a $3,000 differential for a gearbox that we may or may not use in the future? That's a pretty big piece of the puzzle. So is like buying a several $100 block of aluminum to machine the gearbox out of, as well as any of the other, like if you're gonna buy a big old tube of aluminum and stick the MRACs in it. Like all of these things are really big purchasing things that A, will have a long lead time, B, they're really expensive, C, they take a long time to like fabricate once you get them. At this rate, I don't think it's feasible to say that you're gonna build it this semester. Unless like you make a Herculean effort, I don't think it's reasonable to expect that. Yeah.
I just have one question about the test box thing, just to confirm, because I might have missed. Are there going to be like safety procedures for like turning the thing on? Because putting an accumulator, like with all the lockout tagout stuff, like I'm assuming that you're thinking about this, or like hoping you're thinking about that.
Yeah. I'm actively working with the electrical team to figure out the best way to improve all the safety features necessary for the.
Laurel, did you not see the big red button? Justin's got all the bases covered.
I mean, this is effectively it. But I also learned how to turn the big red keys. So.
One thing to note about the Mark IV accumulator is that it's missing a segment. I forget whether the segments in the accumulator are. I think they're wired in series, right? So
it dropped voltage.
Yeah. So you're just keep that in mind. When you're doing that, it's like one segment short of a full accumulator.
That's an interesting note. Thank you. But yeah, I think the rest of this I could probably go over like people like one-on-one in the future. Thank you for the feedback on this so far.
Awesome job, everyone. This might feel like the earliest we've ended a design review. So thank you everyone for sticking with it. I hope people got some great feedback. I took notes on most of the questions that was asked, and like 90% of this was recorded, so I'll be uploading that to YouTube probably. Yeah, thanks so much. Have a nice rest of your week, everyone.
I just want to say you guys all did a really good job. A lot of really good communication, clearly stated goals, great drawings. I love seeing the math and the assumptions. You guys all rocked it. So good job.
Thank you.
Even if we're harsh